Okay. Um, Open AstroImageJ if you haven't done this yet. All right. Let's say it's a pretty slim program, right? This is the main interface window here. This is the main toolbar right here. The very first thing you want to do, this is in the installation instructions. So the link that I sent you with where to download AstroImageJ, be sure to follow those installation instructions step by step. It'll be a little different for your operating system, but the one of the last steps where it has you increase the memory, definitely do that. So allocate as much memory on your computer to AstroImageJ as you can, because it's going to make processing your images later on a whole lot faster. Okay. Um, all right. So once you've done that, AstroImageJ, you're going to go open the file, and here I've got just saved on my desktop. This is the test file, and here we go. All right. So here's the main view. The nice thing about AstroImageJ is it gives you widths here. So this line is 6.5 arc minutes wide. So that's pretty big. The full image, all of these LCO images have the same field of view, which is, I think I said 19 arc minutes by 29 arc minutes, something like that. You'll notice this purple box up here. Here's the whole image. Here's like the size of the whole image. And it tells you, okay, north is to the left, east is down on this image. You can zoom in and zoom out by using these magnifying glass controls. So the one on the left that says zoom in fast is kind of nice because it just lets you zoom in right into the center. Now you'll notice there's this smaller purple box over here. So that's your field of view. So you can move around and it'll move the purple box that shows you what your field of view is. So probably that's our target star. I say probably. We want to be sure, right? If you want to look at a particular star, double check, okay? What are all these numbers up on the top here? So image J, X, and Y, those are the X and Y coordinates for the pixel that your mouse is hovering over. So that's just telling you the coordinates on the image in X and Y coordinates, where, again, the green arrows here tell you X increases to the right, Y increases going down. The more important part here is right ascension and declination. The other important thing about FITS images is that every FITS image has a text file appended to it called a header. So when the telescope takes the image, that the software on the telescope is automatically set up to glue this header onto the image, and the header has lots of valuable information about the image. One of the things that the header has is the right ascension and declination coordinates where this image was taken. So the software here, AstroImageJ, reads off the header and it says, okay, based on what the header is telling me, it can convert the X and Y coordinates in this picture into right ascension and declination coordinates on the celestial sphere. Here's how you read this, right? This is a sort of a standard way to read or to notate right ascension and declination. So remember, right ascension is measured in hours, minutes, and seconds. So those are broken up with the colons. So wherever my mouse was a second ago, that point is at 6 hours, 51 minutes, 51.6 seconds of right ascension, and positive 77 degrees, 14 arc minutes, and 49 arc seconds of declination. Okay, so you want to go and say, oh, okay, that's my target star. All right, you can click on it if you want to. I don't have it set up to do anything if I click on it, but okay. Hover your mouse over that star and then double check, is this the correct right ascension and declination for my target star? It probably is. The pointing on these LCO telescopes is pretty good, but you just want to be sure. Is this the star I'm studying? It's at the right RA and dec. It must be the right star. Okay, this is the one I'm going to study. If it's not, then you need to sort of go hunting around and go, well, okay, which one of these stars is it? Maybe, it's that one. Oh, okay, there you go. All right. Just a good sanity check. You don't want to spend hours studying the wrong star, right? Um, okay. Okay. Um, to measure the brightness of the star, you need to, like we were talking about before, I'm gonna do, here we go. Okay, so um, multi-aperture photometry. Okay, I'll explain this here in a second, but I just want to like paint this on here to show, just to show the point. All right, we're going to draw three apertures, three circles around that star. All right, the software is going to add up all of the light from inside the inner circle, and that's inside this inner circle should be the light from the star, but it's also going to be the extra light from the sky. Then, in between the second and third circles, the software is going to sample how bright the sky is. And then it's going to subtract off, by measuring how bright the sky is, it's going to subtract the light from the sky in this inner circle so that what it spits out to us is just the light from the star. Right? It's going to take the light from the sky plus the star, subtract off the light from the sky, and it'll give us the brightness just of the star. Now, that's probably what this number is right here. But, so that number right there, T1 meaning target 1, 5.47 times 10 to the 5th power. That's probably the brightness inside there, but I want to be sure. But also I want to know what the signal to noise ratio is. Okay, how do we do that? Okay, I'm gonna shrink this down for a second. To do the photometry and to have it read off the answers to us, read off the measurements to us. All right. I am going to go back here to the main menu, go to the two circles here that are called aperture, multiple aperture. Click on that. It's going to give you a bunch of settings. As of right now, I think these settings are fine. We may need to tweak these later, but these are the default settings that I'm seeing, and it seems okay to me. Just leave these as is for right now. Go to aperture settings, and it's going to give us, I think, the same thing. So just leave these as is for now. Click more settings. And now it's going to say, all right, what all measurements do we want it to take? Each of these click boxes is a measurement that we could have the software spit out for us. The file name, I unclick this. Yours is going to look different because I was playing around with this earlier. But do I need the file name? No, I don't need the file name. Slice number, nah. Julian date. Julian date is an astronomical way of measuring time and date. You don't need that. Click that off. World coordinates in right ascension and declination. I want that. The X and Y coordinates, no. X and Y coordinates, don't care. Aperture radius, not that important. The source counts, this is what I want, right? I want to know what are the counts from the source. The source, in this case, being the star. What is a count? A count is an electron, right? How many electrons did the light from that star generate on my CCD? So the quote-unquote counts are what we're measuring because the counts are proportional to the flux. All right, so that's our main answer here. The source peak, fine. Sky background, I want to know how bright the sky is because that'll give us a sense of how noisy our information is. I unclicked all of these, but I want to know the source SNR. SNR is the signal to noise ratio, right? The signal is the light from the star. The noise is the light from the sky and all the other error sources. So by taking a ratio of the signal to the noise, you take how much light or how many electrons did we get from the star, how many electrons were generated by the noise. When you divide them, that gives you a measurement of the error, of how good your data is, how reliable it is. The higher the signal to noise ratio, the cleaner our signal is, the more reliable our measurements are. So those are the three main things that I want: source counts, sky background, source signal to noise ratio. Those are the three things we want. I could pretty much unclick all of these. Oh, and the RA and DEC is good just to be safe. I'm going to unclick. I'm going to leave the rest of these as they are because I haven't played with those yet. So I'm going to leave those as is. I click OK. All right. Then I say place apertures. All right. Now I'm ready to do what I just did. I'm going to click on this. Right. If I were doing more than one star, then I could click on multiple stars and click, measure multiple stars at once. But I just want to do this one. So I left click on my star. It places my apertures. Once I'm done and I'm ready for my brightness to be processed, I right click on the image, and then the program just starts spitting out lots and lots of windows. I don't know how to turn these off yet, but the one important thing that we need is the measurements window right here. This is our answer. Oh, and that thing. Okay, we don't need that. So this is all of the measurements for my star. So here's my source brightness, right? 500,000 counts, cool. My signal to noise ratio, 736. So the star was 736 times brighter than the light from the sky and all the sources of noise. So that's a good ratio. That's a very good ratio. The sky per pixel is 1.1. That's pretty nice, right? Basically what that means is that every pixel of the sky is only generating one count. That's a nice quiet background. Ideally, if we could clean up the sky perfectly, it would be 0. But, one compared to 500,000, 1 might as well be equal to 0. So that's nice. That's one of the reasons why our signal to noise ratio is so good, is because the source is so much brighter than our reduced sky. Okay, so on the instruction sheet that I gave you last week, I want you for each, right? For your bright star, your medium star, and your faint star, right? For the bright star, the medium star, and the faint star, I want you to give me the counts. And you don't really need DN. DN is one of the ways of measuring counts in a different piece of software that I decided to not have you guys do, so we can get rid of the DN. I'll just say source counts. Record for each exposure the number of source counts and the signal to noise ratio. Those are the three answers we need for each image. Okay? How will you know which image, right? Is this image of the bright star, the medium star, the faint star, and what's the exposure time? That can be read right off of the header. So if you go up here to this button right here, if you leave your mouse, it'll say display fits header. You click on that, and this is the big text file. This is the big header that gets appended to each image. All right, lots of stuff. It's like, here's the keyword, here's the value. The comment column basically explains what each of these rows is. So what you want to know is column 39. Column 39 is the actual exposure length, or you could go to column 40, which is the requested exposure length in seconds. So this is the image that I requested be taken for 5 seconds. And column 81, that was the name of my request. So Rosenthal, bright, number 5 seconds. So that can help you out, right? This is for Genevieve and Andrea's group, your bright star, your 5 second exposure. So I sort of did this out of order. You could do this first, right? Open an image, open the image, open the header, figure out which star this is. This is your bright star, your 5 second exposure. Make sure that it's your 5 second exposure. Yep, it sure is. Great. Now you know where, okay, so this is the bright star, 5 seconds. Okay, I'm going to write this in here. So then for this star, the bright star for 5 seconds, 545656 is your source counts. So 545656, and your signal to noise ratio is 736. Great. All right, on to the next image, right? You're done with this image, go do the next one. Okay. That's how you're going to fill out this table.